Welcome. Today we're going to learn a new statistical tool called chi-square. Chi-square. Now, chi-square is actually a fun and helpful tool, and my goal is to use Excel to make this a very easy process for you to understand. And so we're going to start by kind of explaining to you what chi-square is, because there are different methods of chi-square. There is goodness of fit method, which we'll do today. And then for the other video, I will show you how to do what we call the independent method. And then we'll also learn about F distribution. Now, what makes chi-square different from other tools is that chi-square is actually in the form of a frequency distribution. And so we want to always test to see if the frequency distribution fits a claimed distribution. That's what makes it different from your other tools like hypothesis testing. And while there's similarities, there's also some differences. And my goal is to explain to you what the similarities are and the differences are. So like I said, chi-square usually comes in the form of a frequency distribution. And so one of the things we do is we always want to know which of our values are observed and which of our values are expected. All right, so you're going to have an expected distribution and also an observed distribution. Now, I want to explain the difference between the two of them. Now, expected distribution of frequency, right, is expected. So think of it as something that's always been, right? While an observed frequency distribution is when you do a sampling, and then your results from that sampling is used to test to see if that expected value is true or expected frequency is true. Now, let me give you a simple example so it makes sense. Now, in the goodness of fit method for chi-square, what we're going to do is to check, right? We want to see if what we observe is the same as what has been expected. Now, let's assume that what is expected is that with teenagers, right? 30% of them love going to the mall, right? 40% of them love traveling, right? And let's say 10% of them like swimming, right? And this is if they have been asked what activities they like, right? And so these are teenagers saying what they like. And for fun, let's say that school, right? Let's say for fun that they say they like to go to school. That's their fun thing to do, right? Now, this is an example of what is expected, right? It's an expected frequency, and you can see it adds up to what? 100%, right? Because as you remember, the sum of total, your relative frequency or frequencies usually add up to 1 or 100%. Now, let's assume now that I want to make sure, or just want to test to see if this is true, right? And so what I'll do is I'll go to a place where I can see students, and I ask them, okay, tell me, what is your favorite thing to do, right? And let's say I have 30 students, and I ask them, right? And I ask them, I give them options, right? Mall, traveling, right? Swimming, school, right? And so let's say, for example, 5 say they love to go to the mall. Let's say 5 say they like traveling, right? Let's say 15, they like swimming, and then 5 say they love school. This is from a sample, right? This is a sample, basically. This is a sample. And so this result is called observed, right? So what we can do now is we're going to try to compare our observed to our what? our expected. Remember, our expected says that when you come across, or if you survey teenagers, 30% of them are going to say they love the mall, 40% of them will say they love traveling, 10% of them will say they love swimming, and 20% of them will love what? School. So it means that if I had these 30 students and I'm using expected frequency, my expected value will be 30% of 30 students, 40% of 30 students, 10% of 30 students, and 20% of 30 students, which means what I'll get, I'll now compare to what is observed. And if there is enough to prove that there's a difference, then I can reject it. But there's not enough, then I will fail to reject it. Now, I know that that's still a little bit wonky, right? Still a little bit confusing. So let's break it down and make it even more, or let's make it easier for you to understand. So let's use a simple example. Now, let's look at this, right? This is what we call the distribution of tax preparation methods. So look at this. This is what we call our expected frequency. What this means is that if you ask people who helps them or who has helped them in the past to do their taxes, usually 25% of the population or of adults will tell you they had an accountant. 35% will say, hey, we use the computer software. 20% we said we did it by hand. 5% we said, hey, we use family or we use friends. And then 15% we said we use a tax preparation service, like, any of these tax offices that you see across the street, right? That's what that's what you should expect people to tell you. Now, what happened is this is how things usually are, right? From past results. Now, TurboTax, what they've done is they now ask 300 adults, right? Ask them how they prepare their taxes. And this is the result they got. 71 of them said they use an accountant. 101 say, hey, we use a computer software. 40 said they did it by hand. 35 said it was family and friends. And 53 said it was tax preparatory services. So this is the result from taking a sample, right? And so this would be your observed. So this is the observed, right? These are your observed values, right? If you add this up, you come up to this 300 that we have here, right? Now, this is the result that you got. Now, remember, right, in expected frequency, what it's telling us is that if you ask 300 people, 25% of them will say they use an accountant. 35% of them will say they use what? A computer software, and so on and so forth. So let's go ahead and create our expected distribution. So what the expected distribution is saying is that if you ask 300 people, right, the number of people that will say they use an accountant will be 25%, right? And so we'll put enter. So you can see this is a little bit different, right? This is what it's supposed to be. It's supposed to be 75 people out of 300 we say they use an accountant, but in this case we have 71, right? Let's do that for the second one too. 300, right? 35% of them we say they did use the computer software. So we'll click on that. Now we're just going to go down the lane, right? So to make it easier for us, we're going to make this hold this constant, right? Or press F4. If you're using a PC, if you're using a MacBook, I think it's Command T as in table. You press enter. and that allows you to drag. So this is expectation or expected. What that means is you are supposed to have 75 people out of 300 say they use an accountant, 105 say they use the software, 60 say they did by hand, 15 say they use family and friends, and 45 say they use a tax preparatory service, right? If you add this up, right, it would give you 300, right? This is what is expected, but this is what you observed. So this is very important for you to tell the difference, right? So this is expected based on what has always been. This is observed because this is how you went ahead and you did your own survey and your results came a little bit different from what has always been expected. So this is how the goodness of fit method works. So now that you now understand what an observed value is or distribution is, and what an expected distribution is, let's go ahead and solve a few questions. All right, so I'm going to click next slide, and you can see what the next slide is. It's the same thing we've done. The only difference here is that we now have a slight change that has now turned this into a question that we have to find. It now says, same thing we have, but it now says, at your level of significance of 1%, you're told to perform a chi-square goodness of fit test to test whether the distributions are different. So we are going to try to see if our distributions are different. And this means our observed as well as our expected, right? So it's the same question. The only thing is that now in the first part, I only showed you how to find your expected distribution, right? To tell the difference between what is expected and what is observed. Now that we know the difference between the two of them, we can now try to see if the difference is wide enough for us to say that these two are different, or if the difference is not wide enough for us to do that. Now, a couple of things. One, the chi-square is a right-tailed test. So it's always going to be right-tailed. So that's one thing that we need to all know. Secondly, so let's make that first, chi-square is always right-tailed. That's one. Two, with a chi-square, right, your degrees of freedom, right, is actually k minus 1, and where k stands for your number of categories. So think of that as, 1, 2, 3, 4, 5. That is your number of categories, right? That's how we find our degrees of freedom. Now, with solving questions involving chi-square for goodness of fit test, there are a couple of steps that we follow, right? And so the steps we follow, first of all, we want to always take our null and our alternate hypothesis, right? We always want to know what our level of significance is. And once we have those values, right, then we can go ahead and find what our critical value is. And from there, we can find our p-value, right? And once you find your p-value, then you can now make a decision, right? So you compare your p-value to your level of significance, and then we'll make a decision based on H sub O, right? Either to reject or fail to reject H sub O, right? So we'll now make a decision. All right, on H sub O. And then we now interpret our results. Right. So these are the steps that we follow. And so we're going to follow this step in solving the question today, right? So let's take it step by step and see how we can solve this question. All right. So just like we did in the past one, right? I'm going to start by saying that observed, right, is this. And remember, right, we said our expected. If you remember what we did was we said our expected would be, this is the frequency, right? We're going to turn it into a distribution. And so we'll say this is going to be equal to, the total was 300, right? And we'll say multiply by this. And then because we're going to multiply all these values by 300, we had to make this static, right? And hold it firm so that we can drag. And just to confirm, we know that the sum of this will give us 300, right? So we've got observed and what I expected. So remember, what they're asking us is, are the distributions different? So is your observed different from what is expected, right? We can see the numbers are slightly different, but are they significant at what? 1%. And so that's what really counts. So let's take it step by step. We're going to take it step by step. So the first step says we should state our null and alternate hypothesis, right? So we're just going to come here and we're going to say, okay, it's of O. We're going to say, all right. In this case, the distributions are the same, right? So this is saying that the observed and the expected distributions are the same, right? And it's of A, right? I'm just going to do this to save space, to save time. Different, right? All right. So you can see the difference between this topic and your regular hypothesis testing of a sample, one sample, two samples, is that there is no mean here. There's no population mean here in this scenario. And that's the key difference. So we've done our step one. So I'm just going to go ahead and do a victory lap and say, this is done. All right. Step two, level of significance, which is given as 0.01 right here, right? So that is also done. I'm just going to come here and I'm going to do level of significance. I'm going to write 0.01. So we've done with that second part. Third part now says we need to find our critical value. But one of the things you want to do before you find a critical value is to find your degrees of freedom, right? And that's very important to do our degrees of freedom. And we know that our degrees of freedom is the number of categories that we have, right? Minus one, right? And so you have 1, 2, 3, 4, 5, 5 minus 1. And so that makes it easy for us to solve that, right? So we can decide to find that, right? So that will be equal to our count, right? We're going to count this minus 1. And so we know we have 4, right? And that's our degrees of freedom. 1, 2, 3, 4, 5 minus 1 gives us 4. All right. So we got our degrees of freedom. And that's going to help us because with that, we can then find our critical value, right? Now, the way we write our critical value, even when we need next, I just want to show you how we write it. So a chi-squared will write our critical value looks like this, right? So we're just going to come here and write our critical value. And remember, right, the critical value is the boundary where we either reject or we fail to reject. And so it's a very important and crucial part of our work. So we're going to do that as equal to, you're going to type in your chi-square, right? And it's your inverse right tail. And so it's asking us for the probability, which is 0.01. And then it's asking us for the degrees of freedom. So press enter. And so we got our critical value as 13.2767, right? So think of that as, and I'll show you what I mean, what that means. Remember, this is a right tail test, so it's going to be right tail. So think of that as something like this, right? It's right-tailed. And so we're going to say critical value, right? This is 13.277. And so what we're doing here is, right, we're going to reject anything here, we reject 8 of O, and anything here, we fail to reject 8 of O, right? And so this gives us our critical value. Now, we can now go ahead and find our p-value. Remember, that's the next thing to find, our p-value, because we have found our critical value. So now I have to find out a p-value. And for that p-value, actually, we do equal to, we type in, we do a chi-square test. And so you can see it tells us to compare actual range and expected range. Actual range is your observed range. Expected range is obviously your expected range, right? And so we'll select this values, which is your actual range. Then we'll select the expected. And so once we hit enter, it gives us our p-value. You can see, right? This is basically times 10 raised to the power minus 7, right? So that's a lot of zeros, right? 0.00000 and then 4. And if that's a number that scares students, sometimes I always tell them it's actually very easy. Come here, select number, and then you increase your decimals, and then you can see that's why you had a 10 raised to the power of minus 7. So 1, 2, 3, 4, 5, 6. So the 7th one was right here. All right. So now that you have that, right? So we've done with our p-value. So now we can compare our p-value to our level significance, right? And so in this scenario, right, remember, to make a decision either to reject or fail to reject A sub O, we usually compare our p-value to our level significance. So you can see in this case, p-value, the level significance is what? It's right here. It's 0.01. So you can see that your p-value is less than the level significance. And if you remember, right, when p-value is less or equal to level significance, we usually do what? We reject A sub O. When your p-value is greater than level significance, we do what? We fail to reject A sub O. But in this case, it is less than, so we reject A sub O. Now, you can also find your test stat, right? If you want to find your t-stat, you can also find your t-stat here, all right? So let me show you that as a second option, right? So to find our t-stat, so remember, we've already rejected, so we've compared here, and we've already rejected A sub O, but we can also find our test stat. And just to equal to, we type in our chi-square right tail, where it says probability, we put our p-value, we put in our level significance, your degrees of freedom, and we press enter. And you can see it gives you 35. That's a huge number, right? That's a huge number. Remember, 13 is the critical value, right? So 35 will be somewhere here. See, your t-stat is 35.12. So you can see clearly your test stat falls in your rejection region. So you can use this to state your decision, or you can use this method. So we can say, for example, we can say since p-value is less than the level of significance, we reject A sub O, right? So we've done the sixth part, right? So that's one way to do it. Another way to do it is to say that, to state what happened here, right? T stat fell in the rejection region, or it's greater. So this is the right tail test. We can say our test stat is greater than the critical value. So we reject A sub O, right? So that would also serve the same purpose, right? And so we can state that and we will be fine. And our test stat is actually written this method. So this will be written in this format. That's a sign for it. So you can see in this case, we have rejected A sub O, right? So what does that mean? Remember, A sub O says that they are the same. By rejecting, we're saying that what? They are different, right? So now we can conclude that, right? We can come to the interpretation. And I know I just made a whole mess of my whole board, but I'm going to make space here to interpret my results, right? I'm going to make my space here. So I'm going to say at 1% level of significance, we have sufficient evidence, right, to conclude that the distributions are different, right? And we're done. So that's how easy this is. And so what you're doing here is the whole essence of the goodness of fit method is that a known distribution is provided or has been provided. You now make an observation by sampling, and then you compare your sampled results to the known expected results. And by doing that, you want to see if what you have is different from what has been, right? And that's how we solve questions involving the goodness of fit test. I hope that makes sense. I'm going to try one more example just so that you feel more comfortable with this topic, right? Because we addressed all these X areas. So I'm going to try one more example with you so that you find this topic even, much more fun than it already is. So let's look at this example here. See, I told you it was going to be fun, right? Now we're dealing with candies, right? So in this example, let's see if I can pull my, okay. All right. So in this example, a researcher, right, claims that the number of different colored candies in bag of M&Ms is uniformly distributed, right? Let me change this to milk chocolate. So it stays the same. All right. So the researcher said that they are usually uniformly distributed. So when you buy a bag of M&Ms, you get the same colors, right? Brown, yellow, red, blue, green, orange. Now, you decide to see if this is true, right? This has always been a norm. People believe this, right? You want to see if it's true. And so you got yourself a bag of milk chocolate, right? M&Ms, yummy, right? And so you open them and you count them. Tells me you don't really have you have a lot of time on your hands, right? You count them, but when you counted them, here's what you got. The brown ones were 80, yellow ones were 95, red ones were 88. So you got different numbers, right? Or marks, right? So let's see this total to 500. And then that would make sense, right? If it did. All right. So what you had was you had the colors probably, but they were different quantity. And so the question is saying that at a 10% level of significance, you are told to perform a chi-square goodness of fits test to test the claim and the expected distribution, the claimed or expected distribution. Remember, the claimed or expected distribution is what the researcher is saying, that they're supposed to be uniformly distributed, right? So the total was 500, but what were the different colors, right? We can count that, right? So the different colors, I'm going to count that. So there were 6 different colors, right? But you got different numbers. Now, what was expected? So let's find what was expected. The expectation is that if I'm having 500, I should have the same number of brown, yellow, red, blue, orange, and green, right? So that will be equal to, that will be 500, right? Divided by what? 6, right? That's what the expectation would be in this scenario, right? And so what I want to do is to see if that holds true. So I'm going to drag this. So the expectation was that there'll be 83.33 brown, 83.33 yellow, 83.33 red, and so on. Now, we know this is not really feasible, right? But the question is the difference such a big difference that we can say that the claim is not correct? That's what we're trying to do, right? This is what the researcher said, that it should be uniform. So something close to this, right? Now, but we had something that looks a little bit different. So how far off is our result compared to what is expected? That's what we're trying to find. How far off are we from what the researcher said? Is it enough for us to reject what he's saying, or it's not enough for us to do so? All right. So let's start with some of the basics. So we're going to try to make a problem statement, right? So in our A sub O, remember our A sub O is usually going to state that they are the same, and then A sub A will say that they're different, right? So in A sub O, we're going to say that distribution of different colored candies or M&M candies is uniform, right? Just keeping it very light, making the statement without writing too many things, right? The distribution of colored I'll say milk M&M's candies is uniform, right? And then for A sub A, I'm going to say it's not uniform, right? Just sneaking a not there, right? So if we fail to reject A sub O, then we agree with the research that, our notes were not the same, but they're not far off, right? At 10%. A sub A is saying all the numbers are far off, right? And they're not uniform, right? Okay, so that's the first steps. All right, our lower significance, we know that's important. So what we're testing against is 10%. Right? Our degrees of freedom, we know that that's usually categories, right? That's usually the number of categories minus 1. So our categories minus 1. Right. And so now that we have that, right, then we can now go ahead and find our critical value and then our p-value and all that good stuff. So our critical value will now be equal to the chi-square, right here, probability, degrees of freedom. And so we got to 9.21. Now we can go ahead and find our p-value, right? And you can see in this question, in chi-square, especially goodness of fit method, you're going to see that there usually is no need to find your test stat. And the reason is because you have to find your test stat, you have to find your p-value. And once you find your p-value, you wonder, why do I need to do my test stat? You can only do that just to verify, just to double check your work, but usually you don't even need to do that. And so this will be equal to your chi-square test, right? Which checks the actual range and expected range. So your actual range is what you had. The expected range is what has always been, right? And you can see that's high, that's 0.69, right? Remember, your level of significance is 0.10. So you can see that this is greater than, right? And remember, once your p-value is greater than the level of significance, usually we do what? We fail to reject. Now, if you are someone who likes test stat, you can always do test stat to check yourself, right? And let's do test stat, and that would help us see if what we're saying here makes sense. And then we do, see that? Remember, this is a right tail, right? It's a right tail. And remember, our critical value is, right, is 9.236, right? And anything here, we're going to reject, right? Anything after 9.236, we're rejecting. So we reject A sub O here. Well, anything here, we do what? We fail to reject. But look at what our test stat is, 3.016, right? So it falls somewhere here. So our test stat, right, clearly is 3.016. So you can see that our test stat, right, is less than a level of our critical value. And once it's less than that, we fail to reject. So in both methods, you can see we fail to reject. So we'll now say, why do we do that? Interpretation, right? You know, say at 10%, right? Level significance. Right? There isn't enough evidence to reject the claim, right? And we can see clearly that we didn't have enough evidence to reject the claim, and the claim was that they are uniform, right? We're not able to reject that because clearly the difference between them was not much enough for us to do so. That's how chi-square of goodness of fit method works. I hope this makes sense, and I hope that you're able to do it easily, having seen how I've solved these questions. For a chance for getting extra credit, you can try question 7, question 9, and question 13. Thank you, and have a great day.